Hello, everyone.
Hey everyone.
What's up, Sam? What's up, Tanit?
How you guys going?
I'm going pretty good, actually.
Oh, that's nice.
I've got a interview coming up, a job interview for MongoDB coming up tomorrow. So pretty nervous
Oh,
about
cool.
that.
Good luck,
Especially
dude.
since I've basically never worked with databases before. So
I mean, I feel as though, if you're good at competitive programming, you're going to be fine with databases.
mm-hmm. Uh,
What type
to an
of a job
extent,
is
to an
it,
extent.
do you reckon?
What type of job? I reckon they don't always say clearly on the actual job application form. It's always just like, you'll be working together with a team to implement products that will have a real impact on the company or something like that. Yeah, I don't know. Honestly, it could be anything. It could be on the database themselves. It could be like software to help the development of databases, like visualization stuff. Honestly, I don't know.
Yeah. Because I last year when I was looking for jobs and stuff, I did apply to MongoDB, but I think I was a little bit too late. But
Mhm.
exactly like you said, the kind of descriptions and stuff they give are very ambiguous.
Yeah.
But I was talking to someone that worked at AWS to do something with databases, I think, and they said that a lot of algorithms work. So I think you'll be just
Mhm.
fine for the interview. Is this your first stage one?
I've been to. I applied at the beginning of years to like a lot of different things.
Yeah.
But unfortunately, I didn't get accepted. So this is my sort of last chance, I guess. Probably not my actual last chance, but one of my last chances.
Oh, yeah. I mean, like, I feel like that's the thing, right? Like, even if you do well at the start, like at the, programming questions, whatever you have, it's so
Mhm.
subjective. Because
Yeah.
a lot of people know the recruiters or something, and so obviously they'll get more preference, which kind of sucks.
Hmm. Yeah, I'm so salty as well. I got like a couple offers, then
Uh-huh.
I turned them all down for to try and get into Google, and I didn't make it into
Oh,
Google, so now I've
dude.
got nothing.
Damn.
Unlucky.
I rate the confidence though. But hey, I think you're good enough to get into Google. I reckon they're silly not to take you.
Yeah, I checked in the final step. I reckon I could. I reckon I could have done it. I could have done it if I changed up my strategy a little bit.
Right.
But
Where do you
that's in
think
the
you went
past.
wrong?
I think so. I made it into like the final interviews. I was going to interview for the project itself.
Mm-hmm.
So the team, or the person who's leading the project interviewed me and told me about the project and stuff like that.
Mm-hmm.
And at that point, I pretty much kind of assumed that I'd already, like I was like basically there. So I didn't really try as hard to like sell myself. I kind of assumed that by the time I made it here, I've gone through like multiple interviews. I'd have been
Yeah.
like, they would have been aware of my abilities and stuff like that. But then in retrospect, I kind of feel like I could have done a lot more to sort of push myself, as in like show why I would have been great for this job, why I have the skills for this particular project in itself. And so I think by doing
Yeah.
that, I would have increased my chances a lot.
Oh, dude, that's okay. You live and you learn, and you're
Mhm.
not graduated yet, so you got heaps more time to
I've
apply.
still got time. Mhm. So how are you guys? How was contest one? What are your feelings about that?
I guess no one's gonna answer. I thought it wasn't too bad. I got stuck up on question 5, but the rest were okay.
Damn. All
What
right.
did
Made
you
it through the
guys
first
think?
4 questions. What do you guys think? Yeah, type it in chat. How do you guys feel about it? Right now, time Q4. That was the election, I believe. Yeah. Fair enough. I think you guys find question 3 hard to implement or annoying?
What's question 3? Oh, the chess one.
Yeah, the chess one.
Oh, dude, that was such a pain.
It was such a pain.
So many edge cases.
Yeah, for sure. You have to like handle like each of the different pieces like separately as well, which is quite annoying. I feel like the sample code for it was like very long as well. Neat says,
Yeah.
yeah, you can ace the algorithm interviews. Yeah, that's one of the things about competitive programming. It basically lets you ace like every single algorithm's interview, like that you do. So algorithm interviews are like a breeze for me right now, which is very nice. You get the chess and later ones. Fair enough, fair enough. All right, if you guys don't know, I guess I'll show you guys. There's actually an editorial. So if you go onto the course website, go to the posts, and you can find an editorial for contest one here. And basically this will tell you solutions for all of the problems, as well as like implementation notes, as well as reference solutions as well. So definitely a great resource to do if you didn't get all the problems of the contest, is to go back and do that thing of solving that we talked about last week, which is basically go to that one problem that you weren't able to solve and just have a read of the solution, make sure you understand it. And that way you just get a little bit better. And then next time, hopefully you'll make a little bit less mistakes and you get one extra question. Okay, so it is now 1:08, so it should probably be a good idea for me to get started. So hello everyone, welcome back to another week of Comp 4128. Today is going to be the data structures tutorial. So quick hands up, who watched the lecture yesterday? Once again, okay, if you haven't, I just want to get an idea of how many people have watched the lecture from yesterday. Oh boy, no hands. Oh, one hand. All right, Tanit, you're the good boy of the class. Very nice. Good boy or girl. Okay. Yes, so yesterday's lecture was about data structures. I guess I should take some time to fill you in. In fact, we actually learned a ton of data structures. I will show you the slides just to give you guys an idea of what's going on. So here is the data structure slides, and on the left you have the table of contents. And you can see there's a ton of different stuff that we learned. We learned vectors, stacks and queues, sets and maps, heaps, which are priority queues. Somewhere in here, there's also order statistic trees as well, union find, as well as range trees as well. So there's going to be a ton of things that was taught in the lecture. Obviously, I don't have time to actually go through all of them in today's tutorial, but a couple of the common ones, and we'll see how to implement them. But if you want to see the whole thing, if you want to get an idea of all the data structures, you're definitely going to have to go through and watch the lectures in its entirety, not just the first hour, because there's a ton of very, very useful stuff in here. But yeah, before we get into today's questions, let's actually just take a look at some basic data structures, some basic concepts about coding data structures in C++, and then we can have a look at applying those to some problems. Okay. Let's start with ds.cpp. Okay, let's go through a couple of basic ones. There's a couple that I wanted to cover, which are more common than others. The first one I wanted to do is vectors. But first, let's do the iostream and csdir. This is for C and cout. This is for printf, scanf. The first thing I wanted to cover was vectors. So vectors are essentially a vector array. These are arrays that can be resized, and they can also remember what their size is. The way that we declare a vector is by syntax. So on the left hand here, this is the type, and on the right hand here is the name of our vector, in which case I'm just going to call it v. So immediately right off the bat, if you're new to C++, the syntax might look a little bit weird. Why is there an int here, and why is it inside angle brackets? Normally when I define something, it's just like the data type, right? So the thing about C++ is that we have these things called templates. And what these templates allow us to do is that they actually allow us to declare things of different types. If you've ever done Java for the object-oriented course, then this should be familiar to you. This is basically the equivalent of generics in C++. And so what this means is that here, vector int, I'm defining a vector which stores integers, but it could actually store other stuff as well. So for example, if I wanted to store characters, I can make it do that. If I want to make it store floats, then I can also make it do that as well. Just make sure that you define whatever type that you want to store inside those angle brackets. And so some of the things that you can do with a vector are, or some of the most common things you can do is pushback. So pushback is putting onto the end of the vector. Initially, our vector is empty, but we're just going to, we can push onto the end of it. It's kind of like an append onto a list in like Python or something like that. So v.pushback, another great thing that you can do with vectors is that vectors store their size. So you can access the size of a vector by using v.size. And so one real natural way that we can use this is to just loop through a vector by, instead of going from like 1 to n and having to store a separate variable separately for the size of your array, the vector itself will store its size. So in this case, v.size is going to be 3. And so we can just print out everything inside our vector like this and exit as all. Also, accessing the vector is exactly like accessing an array. You can use the square bracket notation, and that will just access the ith element in the array. So this sort of for loop here is just going to print out every single thing inside our vector. So let's try this out. A lot of errors. Vector is not declared up using namespace std. Don't forget to use that. That's another one of the quirks of C++. So in C++, there are these things called namespaces. These are here so that you don't confuse the names of things with like other stuff. Typically, what you would have to do is you would have to type in an std : before anything that's in the standard namespace. But since we're competitive programmers and we don't really care about style, we're just going to put a using namespace std at the top. And that way, that's just going to apply it to everything. So here's a warning. It's telling us that v.size is a size type, whereas I is an integer. We can just convert it to an int to silence that warning. But apart from that, we can see at the bottom that we print out the contents of our vector. Okay, if you want to look at some of the other stuff that vectors can do, I won't go through all of them, of course, because I don't have the time. But just quickly do a search for vector in C++. Go to c++.com or CPP reference, both are great. And if you scroll down, you should be able to see member functions and just all the different things that you can do with a vector. So you can recognize a couple of these. So push back here, add an element to the end, as well as the square bracket operator, as well as front and back if you want to access the first and last elements. And size should be somewhere here as well. Yeah, up here, size. So those are some of the aspects of the vector. Okay, next thing I wanted to cover is, let's go with iterators. So iterators, these are a C++ concept once again. And basically what these allow you to do is they allow you to loop through a data structure. So you can kind of think of these as pointers to a particular data structure. They're not exactly pointers, but they actually share a lot of similar properties with pointers. In the respect that they will point to an element, and you can actually, for at least some of these data structures, you can actually increase or decrease the pointer or the iterator to go to the next element or the previous element. So one really, really nice use case of this is to loop through the array again, but in a slightly different way. So this time, what we're going to do, we're going to define an iterator. This iterator is going to be in our iterator header. So make sure you include that at the top before you use it. And then over here, what we're going to do, I think the syntax is this. So vector int iterator it. So this is the iterator data type. I'm going to find an iterator called it. What I'm going to do, I'm going to set it to v.begin. v.begin returns an iterator to the first element in our vector. And then what we're going to do, while it doesn't equals to v.end, we're just going to increase our iterator by using it++. And I'm going to print out whatever is pointed to by our iterator. Just like a pointer, we have to actually dereference it. So we need to put that star notation at the front in order to convert that iterator back into an integer for us to print out. And finally, we can do that /n at the end as well. So if I run this, hopefully, if I did it correctly, it should do the exact same thing as our for loop up here. And that's just to print out the contents of the array. One final thing. Yeah.
Sorry, I just had a quick question. For vectors, I know that in order to initialize it, it's a constant time operation, OFN. So when we're using vectors for like a contest or something, would you recommend that we initialize it just like we'd initialize an array outside the main scope?
It doesn't really matter where you initialize it. You can. What do you mean by outside the main scope, by the way?
Oh, right. So sorry, I just meant like, should we initialize it at the start with the size equal to the maximum amount of input so that we don't have to expand it every single time?
It's completely up to you. It doesn't really change that much. The complexity, which is always going to be order n, regardless of whether you initialize at the beginning or you just keep adding on until you reach your input size.
Right,
So
okay.
Completely up to you.
Cool.
Okay, the next thing I wanted to cover is sorting. So this was actually one of the mistakes that a couple of people made in the contest. That, as well as forgetting to use longs was another really common one. But yeah, so sorting in C++ and in competitive programming, we don't actually need to write our own sorts. So a lot of you might have come from like 1511 or like some of the earlier computing courses in C, where we had to code our own like bubble sorts or code our own sorts. But that's not really the case with C++. We have actually functions that do that for us. So at the top, what we're going to do, we're going to import the algorithm library, which is a very useful library. And then at the bottom here, what we can do is we can just sort, and then the arguments we're going to give in is going to be the start and end of our data structure. So for a vector, this is going to look like this. It's going to be the iterators to the beginning as well as the iterators to the end. If I have an array, then what you can do, the syntax would be a and then a plus 1000, or the size of the number of things that you want to sort. So this is going to sort the first 1000 things in our array. For vectors, this is going to sort the entire thing. And so, yeah, this sort function is going to sort, it's going to sort your serving for you. It's going to be order n log n. And so you don't have to worry about the specifics of actually coding up your own sort. It should be as simple as just using a library to do it for you. And of course, this is allowed in contests as well. You're completely allowed to do this. If you want to sort in reverse order, you can pass in greater int like this. But I like to do just reverse b.begin, b.end. So sort it and then reverse it, because I'm lazy and I don't really like to remember the syntax. So you can just sort it and reverse it. And that's a good way to sort in descending order as well. There's also ways to write your own custom comparison functions. I'm not going to do that today. You can search it up in your own time as well. And I'm sure in the upcoming tutorials, it's going to come up as well. Okay. That's sorting and vectors. Let's move on to sets and maps. So next data structure we're going to look at is going to be the set. So the syntax is the same as a vector. We're going to include the type of the set inside those angle brackets. And what a set is, it's basically implemented as a self-balancing binary search tree. It allows us to insert elements and it allows us to erase elements and find elements in order log n time. So the usage is going to look something like this: insert 3, s.insert 5, s.insert 7, like that. So now our set contains these 3 elements. And then what we can do now, we can also erase them. So let's erase the 7. And what else can we do? Yes, we can find elements as well. So if s.find is s.find 5 does not equal to s.n, then we'll say 5 is in this set. What this thing is s.find. If it finds the 5, then it's going to return an iterator to that 5. But if it cannot find that 5, then it's going to return an iterator to s.n, which is kind of like the it's like the past the last element in the array. It's like a special iterator. So if it can't find 5, it's going to find return s.n. And so if it is not equal to s.n, then we can say that 5 is in our set. That's one way of checking if 5 is in our set. An easier way to do it would be to do s.count5. That's going to return the number of times 5 appears in your set. And of course, if it appears in your set, then this is going to be larger than 0. So if this is larger than 0, then we can also write this out like that. Cool. So those are two ways to count or to check if there is an element in our set. One other cool thing that you can do with sets is that you can do searches on them. In fact, more specifically, you can do basically the equivalent of binary search, and that is to find the lower bound, upper bound of a number. So here we can find the lower bound of 3, and we can also find the upper bound of 3 as well. And so the definitions of these are returns an iterator to the first element greater than or equal to 3. And the second one is the same thing, except it's just strictly greater than. Oh, this is upper bound. And these are both log n time. So this is basically a property of the binary search tree, which is that we can search through our elements like this. And so lower bound and upper bound are both really great ways in order to find certain elements within our set. Tanit asks, S of n is not 7, right? It's not the last element. Yeah, you're absolutely right there. So, well, firstly, 7 is erased. So, but let's assume that our set over here, 3, 5, 7, it's going to look like something like this. Then s.n is actually going to be a special element, which is after the n. So you can almost imagine that your set is 3, 5, 7, and then s.n like that. That's what allows this iterator thing to work as well, because this loop here, since v.n is past the end, then we actually include the last element as well in our for loop. The same here. S.begin, however, will point to the first element, which is 3. So keep that in mind when you are using sets. Okay. Yeah, so I've covered lower bound and upper bound. And finally, one thing I wanted to cover is multi-set and unordered set. So sets have two variants, and so do maps as well. So multi-set, a normal set will only allow you to store each element once. So that means if you insert 7, like if you insert 7 multiple times, then this set, normal set, like this one, is just going to store the one occurrence of 7. However, if you define a multi-set, I'll call it S2, this is going to allow you to insert 7 like multiple times, and they'll actually be stored as separate instances. And then for the unordered set, this is for if you want to use a hash table in your sets. So if you want to use a hash table, then use the unordered set, and this will get you complexities down from log n time of insertion and erasing down to a constant time, because we are now using hash tables. The one drawback, if you can call it a drawback, of using unordered sets is that the elements inside the set are no longer sorted. Whereas with a self-balancing binary search tree, the elements have a sorted order, and if you iterate through them, you'll get them in sorted order. Okay, final data structure I want to cover is going to be maps. So the map is going to look like this. Same syntax as before. Actually, not quite, because this time we need to define 2 data types inside our map. Maps store key value pairs. And so these are going to be the 2 data types of your key, so the first one, and your value, which is the second one. So this map will map integers to integers. You can map integers to strings, for example. So maybe map an ID to a student name, or you can do like, well, any sort of combination of data types. I'm gonna stick with int and int. And basically, the easiest way to use maps is really just to use them kind of like as if they were an array. So what you can do is you can say map of 10 is equal to 3, map of like 20 is equal to 20. And that was map 10 to 3 and 20 to 20. And then you can access them the exact same way. So you can say, okay, print out what's at map 20, and this should return 20, right? So what exactly is the difference between maps and arrays if this is the case? Well, first things first, maps allow different key types. So once again, this could have been a char, and I would have inserted elements like this. So that's something that arrays can't do. And secondly, what you can do is with maps, you can actually, they don't take up as much space as an array compared to the number of elements that you're storing. So for example, I could do this, right? This is like something like 3 million, but the map data structure itself wouldn't actually need to make 3 million slots underneath to store this number. Whereas if you had an array, you would actually need to go up under this 3 million as well. So that creates a lot of space complexity there, which is sort of unwanted. So maps are very useful if you want to quote unquote have an infinite array, as well as all kinds of other uses where you want to map something to something else. Once again, we have the multi-map and unordered map versions as well. And their uses are kind of self-explanatory. And also, once again, if you have any questions about any of these data structures, as well as any of the other ones that are covered in the lectures, go ahead and just Google C++, like multi-set, for example, if you want to learn more about that. And you'll get a very nice list of all the different methods that you can use with a multi-set. Okay, that concludes my very quick sort of rundown of some common data structures in C++ and how to use them. Does anyone have any questions before we get on to the main problems for the day? No questions? Okay, excellent stuff. In that case, let's get started with our first question. So let's head over to the tutorial. Today we've got two questions, ghost encounters and restructuring company. Ghost encounters is the easiest one, so I'm going to start off with that, and then we're going to head off into restructuring company. Ideally, I like to do ghost encounters quite quickly because restructuring company is definitely quite difficult, so we're going to need a little bit of extra time for that. Anyway, here's a problem. I've linked it in chat. Essentially, this is going to be, you have a friend and you're trying to make her see as many ghosts as possible because you are a bad friend, of course. So what I'm going to do, I'm going to give you guys something like, let's give you like 2 minutes to have a read of this question. You should hopefully remember how to read questions from last week's lecture. You should be familiar with all the different parts of a question. So yeah, just have a go, read through this question in those 2 minutes. And afterwards, I'll come back and sort of go through it together. And of course, if you have any questions during this time, feel free to ask them. Okay, has everyone read the problem, or do you guys need a little bit more time? little bit more time? Okay. I'll go through the sample cases with together with like everyone after this time is over. So feel free to skip the sample, playing the sample cases if you want. Okay, so has everyone come to grips with the question now? Okay. Kevin says okay as well. Yep. Okay, so just a quick recap. Basically, you have a straight line trail, right? And Toba's going to be walking along this trail starting from like sometime after sunset. It's going to start walking along. And along this trail, at X meters into the trail and at time T, a ghost will appear at a particular position and a particular time as well, right? And it'll appear only at that position and only at that time. And so if Topa just happens to be at that position, at the correct position, at the correct time, then she is going to see that particular ghost. And they're going to be n different ghosts that all appear at their own positions and their own times. And so our goal is to try and decide what time Topa should leave after sunset in order so that she can see as many ghosts as possible. Let's have a quick look at some of these inputs. So we have N and K. N is going to be the number of ghosts, and K is going to be the number of seconds per meter that Topa takes to walk. And I'm going to get a bunch of X and T values, which correspond to the ghost's position and their times. So let's have a look at this explanation here. So here's our first, this corresponds to the first subtask. So here we have one ghost appearing at time equals to 2 at position 1, and another ghost appearing at time equals to 6 at position 2. And it looks like also another ghost at time equals to 9 at position 9 as well. And of course, K is equal to 4. So what this means is that if she sets off at time -2, then she's going to arrive at position 1 at time equals 2 seconds and see this ghost. Then she's going to arrive at time equals position equals 2 at time equals 6 seconds and see the second ghost. And that's going to be the maximum amount of ghosts that she can see. So the answer for this question is going to be 2, right? So that's how the question works. And of course, we're trying to find that starting time for Topa, which will maximize the number of ghosts that she can see. Let's have a look at the subtask. We have N is smaller than 100,000 for all test cases. N is smaller than 100,000 and K is less than 30,000. The positions are going to be less than 30,000 and the times are going to be less than equal to 1 billion. So this is a big number and we should make sure that we keep that in mind when we're doing the question. Additionally, this might be the first time we've seen this, but this question has subtasks as well. So subtasks are basically easier versions of the question. They're there to help guide you towards the full solution. So if you cannot solve the full solution, but your question has subtasks, definitely invest some time into trying to solve these subtasks because they're going to be helpful to you when it comes to approaching the full solution. Okay, so that's the problem. If we're all up to speed, does anyone have any observations about the problem that they may like to share? how might we solve this problem?
I initially thought that it looked like a graph.
Mm-hmm.
So if you have meters on the x-axis, so
Yep.
the meters, where we see the ghost, and the time that we see the ghost on the y-axis,
Mm-hmm.
then k, which is the cost of, I guess, moving for every meter, would
Mm-hmm.
be the gradient.
Yeah.
And then I think we can calculate that s in this case would be the x-intercept. So we want to kind of see what that maximum value is. So for each ghost time ti, I think we can go ti minus k times m.
Mm-hmm.
And whatever the maximum value of s is, whatever s value has the most amount of, ti minus km's will be the one that we want to use. So I think we can use a map for that.
Yeah. Perfect. That's pretty much exactly the full solution, except it's t minus kx, not t minus km, but minor detail.
Kx, yeah.
Yeah. But yeah, you've got it absolutely right. So let's go through this a little bit slowly, just so everyone else, just to make sure we're all on the same page here. So I'm gonna make my scuff diagram here. And so what we're gonna be noticing here is that we can actually plot these points as a graph. So on the bottom here, we're going to have our x values, and on the top here, we're going to have our t values on the y-axis. And so what this means is that ghosts have a certain position and they have a certain t value as well, right? And what this k basically tells us is going to tell us the gradient, right? The gradient at which Topa will walk at. So Topa here, we're going to pick a time after or before sunset. So this is 0. So maybe at like -2, for example, maybe -2 is here. And so K is going to, the path that Topa is going to walk is going to be like a straight line, right? Because it's linear, it's going to walk the same amount of distance in the same amount of time. And this gradient is given by K. So let's say, for example, K looks something like this. And it passes through 2 ghost points. And what that basically means is that if we start at this particular time, then Topa is going to see these 2 ghosts. We can also affect the time that Topa leaves. So for example, maybe if she leaves later, then the gradient is still going to be the same. K is fixed. And so her path is going to look like this. But this time it passes through none of the ghost points. So this time we're not actually going to see any ghosts. So now our question kind of becomes, how can we work out the starting time for Topa to leave so that this line just crosses over as many points as possible? And the way that Sam suggested was to actually just calculate the starting time that every single ghost would need if you want to see that ghost. The way you can do that is, of course, by starting with a ghost, we draw that gradient K, not gradient gray, gradient K line back to the x-intercept, and we find out this is the starting point that we need in order to see this ghost, right? And we can do the same for every single other ghost as well. So this ghost corresponds to here. This ghost also corresponds to here. I'll draw another circle on the side to indicate that. And this ghost may be somewhere down here. And the formula that Sam suggested is going to be t minus kx for every single ghost. Oops, let's do the capital T to match the question. So the time that you need to leave to see ghost I is going to be t minus kxi. So basically kxi, since it's k seconds per meter and xi is the meter, so this is going to be the amount of time you need to get to this ghost. And so if you want to see this ghost, you've got to subtract that off the time that the ghost appears as well to find the time that you need to leave. So that's the thinking behind that formula. And of course, for every single ghost, you can calculate this value, which is going to correspond to where this point is on the x-intercept. And we'll just find the most common value of this for over all the ghosts. And of course, as Sam suggests, the best way that we can do this, or one of the ways we can do this rather, is going to be using a map. Maps allow us to, once again, count up the number of, like one usage of maps is to, like, for every single x-intercept that we can see here, we can map it to the number of times or the number of ghosts that correspond to that starting time. So this is going to allow us to get to the full solution. So to recap, for every single ghost, calculate this value. store it into a map, keeping count of how many times a ghost will appear given a starting value. And then once it's all stored inside your map, we can just loop through the map and find the one that has the most amount of ghosts that you can see at that starting point. And that's going to be our answer. Does this make sense to everyone? Are there any questions? Yep, got a thumbs up from Tani. Very nice. In that case, I'll just jump straight into the coding then. It's quite a simple problem. So if it didn't make sense in the explanation, I'm sure it'll make sense in the coding segment. All right, ghost.cpp. Okay, so let's put in our header functions like this. None of the vector, I just need a map. That's all I need. And let's also quite a quick explanation. Calculate T-K-X and store that in the map, and then loop through the map and count the most common occurrence. So that's just going to be our solution. And he asks, can we do the bit SED header? So if you guys don't know, there is a header that's called bits SED bits/SED C++.h. And basically this header is like a super header, which imports all your other headers. So if you import this, then you don't need to import anything else. And the answer to that is yes, you absolutely can use that. So this is going to work for certain operating systems. For others, you might need to do some setup. So this works for, actually, I can't remember which ones. I know for Mac, it's not supported by default, so you have to do some extra work in order to make that work, which is why I'm kind of doing the long way and making sure I include all the headers separately. But absolutely, if your machine supports this, then absolutely use this. This is going to be fine. I believe the contest as well. So when we're doing the course contests, they should support this. So you should be able to use them, no problem. But some of the judges on the problem set don't support bits SED C++.h. So a couple of them don't. Most of them do, but some of them don't. So you just have to be a little bit careful if you're going to be using this, because some of the problem sets might give you a compilation error, and you might then have to actually manually insert all the headers like this. So it's good to actually know what headers are which and what's getting stored in each of these headers. Okay, so hopefully that answers your question. Let's go into this problem here. So we need to scan in N and K. Okay, like this. Then we need to scan in all the ghosts and their X and Y types. So times. So let's loop through like this. Let's keep a map. So I'm going to map from int to int. So sorry, as an M like that, this is going to just keep track of how many ghosts of every single starting point there are. So map starting points to number of ghosts. One cool thing about C++ maps is that if something is uninitialized, its default value is the 0 value. So it's going to be 0. So this map is kind of already initialized to 0, which is very nice for us. Okay, so we're going to scan in X and T like this for this particular ghost. I'm actually going to use lowercase. That's more of a style thing, up to you. And then what we're going to do, we're just going to insert it into our map. So map, we're going to use our formula here. So T minus K times X plus plus. This will just increase the count by 1 for this particular starting time. And so finally, after we finish this for loop, we should have all the starting times recorded inside our map. And so now it just becomes an issue of trying to find the most common thing in our map. And the way that we can do that is to actually, one of the easiest ways to do that is to actually just loop through our map. I'm going to use a little bit of a new syntax here that you might not be aware of. And that's going to be called the range-based for loop. So one way we could have done this, oops. Okay, so one way we could have done this to loop through our map, we could have used our iterators, right? I showed you how to do this in here. So you start an iterator at m.begin, and then we just loop through like this. But there's actually a very nice C++ shortcut that allows us to do this for us. And that's going to be using the range-based for loop. Firstly, let me explain this part. This pair in int is going to be a paired data type. Basically, all it is it allows us to define a pair, and a pair is just a set of two elements. So you can access the first part and you can access the second one. It's a pair of elements. Pretty straightforward. Since maps store key value pairs, we need to use a pair in order to loop through our map and get all the keys and all the values. And then this notation here is going to be the range-based for loop. So here, what we can do, we define a data type and then a variable name. So our variable name is going to be p. And what this is going to do is just going to loop through every single element in our map. And it's just going to set p to be equal to that particular element. If you're familiar with Python, this is basically identical to doing something like this. So for I in array, then if you use this syntax, then I is going to be set to each of the elements in the array. Same here. So p is going to be set to each of the key value pairs in our map. So what we can do, answer equals to 0, answer equals to max of answer, and p dot second. So remember, second is to access a pair, we can use p dot first and p dot second. And p dot second is going to be the value, right? The number of ghosts. And for this particular question, I believe we're just trying to find the maximum number of ghosts that Topper can have. That's why we'll just take the maximum answer, p dot second, and answer. Another cool thing that I want to explain is this max thing here. So max, firstly, I need to include a library for this. So this is an algorithm. So algorithm also includes the max function. Max takes in two things, and it returns the maximum out of the two of them. So in this case, normally if you are using C, then you would type something like this. So if p dot second is larger than answer, we're going to set answer equals to p dot second. That's how we normally do it. But in C++, we can do it in one line just by setting answer equals to the maximum of itself and p dot second, the thing that we want to take the maximum of. Very nice, quick shorthand that allows us to find the maximum of something in one line. And I think that's pretty much it. After that, we can just print out our answer here. So let's try this on a couple of sample inputs. Oops, I need to go into Ghost and run that. Output is 2, which is correct. Let's run this one as well. Output is 2, which is correct. And finally, run this one as well. Output is 3, which is correct. Okay, so it looks like our program is working for all the inputs. If this was a contest, you would then go on to submit it and check to see if it works. And of course, if there's bugs, then start the debugging phase. But in the interest of time, I'm just not going to do that for today. And I'll just leave it as is. And we can just trust that it works. You can take my word for it. I've done practices on this, so I can just tell you this is working code. Okay, are there any questions about this code then? Or about the problem itself, the problem solution, or this code? Are there any questions? Give you a little time to type it out.
I had a question about the range-based for loop.
Mm-hmm.
Are there any performance costs of using this? Like as opposed to, I mean, I can use it for arrays and vectors and stuff. Is that a valid way to do it?
There are no performance costs. So it's going to be linear in terms of the size or the number of things inside whatever data structure that you have.
Right.
Which is going to be the same as if you had to do a for loop for it anyway.
Okay.
One thing you do have to keep in mind is that you can't really use this for arrays because arrays don't actually have iterators and they don't actually store like their size. So trying to use a range-based for loop on an array is not going to work. Something like this. Let's actually make this something. This is not going to loop through the first 100 elements because C++ program, I think, doesn't actually know where to stop if you do something like this. So it doesn't really know to stop at 100 or where. So don't do it on arrays. Only do it on these data structures like vectors, sets, and maps.
Cool.
Okay, awesome. One final thing I did actually want to do before I move on was just do a long check with you guys, because again, as I mentioned before, this was a issue with the contest. Some people forgot to check their longs. So let's do a quick long check and let's double check that we didn't actually need to use longs in this question. So firstly, the difference between ints and longs, if you weren't aware, integers, they look like this. They store up to values of 2 billion. So integers are up to 2 bill, which is 2 to the 32 or 2 to the 31, I think, something like that, -1. Whereas longs, they can store up to 10 to the 19, which is corresponds to 2 to the 63 -1, something like that, right? So for certain types of questions, an integer isn't going to be enough to store the values. Sometimes the values get very big. And so you might need a long in order to store the values instead. This was true for question 5 of the contest. So in question 5, in Illuminate, some of the input values went up to 10 to the 18. And so that's why you would need to have to use longs in order to store those values. Let's quickly show you guys how you can check for longs before we move on. The way you check for longs is, of course, you just double check the possible value ranges of all your integers, right? For example, n here, n's going to be smaller than, from our constraints, n's going to be smaller than 100,000. So we should be pretty safe there. The big one is going to be time. And so the one part that I'm going to be worried about is this formula here, t minus k times x, right? Because maybe this value actually drops outside of 2 billion or -2 billion, since this could be negative as well. Let's do a quick double check here. K and x, so k is less than or equal to 30,000, x is less than or equal to 30,000. So multiplying the two together, you get 900 million, which is, we'll just round it up to a billion. Just so I'm going to be a bit fuzzy here. So this is about a billion, 1 billion. So the lowest value of t possible would be 1. So 1 minus 1 billion would be -1 billion, which fits inside an integer. Great. And the largest value this could be is this was 1 billion, and then this was 1, right? So both k and x are 1, then this would be this maximum value. But then that would still be up to 1 billion, right? So t minus k times x, really, its range is going to be between 1 billion and -1 billion, which means it's going to actually fit inside an integer. So we don't actually have to worry about it here. Same for our answer as well. Since all of these values are going to be fitting inside an integer, then we don't have to worry about the maximum being greater than an integer. It's still going to all fit inside an integer. So for this particular question, where we don't need integers, if for some reason we calculated this to have a range greater than 2 billion, then of course you would need to consider using longs. And the way you do that is just, instead of using ints, you use a long instead, and long here as well. Okay, that's pretty much it. Are there any questions about that? I think it's pretty straightforward. Not too much of an issue there. This would be something, a little bit of a mental check that you should do before you submit any question, really, just to double check if you need longs for this particular question or not. Okay, let's move on to restructuring company. Second problem of the day. I once again linked it in chat, and once again I'll give you a solid 5 minutes to have a go up until 2 o'clock to have a read of this question. Once again, if you have any questions, feel free to ask them in chat. Okay. Is everyone okay with the question? Or do they need a little bit more time to read through it? Okay.
So I was just wondering what happens when a team is merged. So if Team X and Team Y are merged, then what's the resulting value of the team?
So they both become the same team then. So for example, if you merge Team X and Team Y together, then the values of Team X and Team Y become the same team. So don't think of this as a function that returns a value per se. Rather, it just returns the team that X is in. You can kind of think of it like a team object or something like that.
Right. Okay.
And all that really matters to us is whether if two people are on the same team, then the values are going to be the same. And if two people are on a separate team, then these two team values are going to be different. That's all that really matters.
Yeah. Yeah.
Okay, so hopefully you've had a little bit of time to digest the problem. I'll go ahead and also explain it myself as well. So we have a large software company. There are N people, right? You can think of these N people as like standing in a line. So maybe something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and they'll be labeled their corresponding IDs. And everyone is initially on their own team. So person 1 is in their own team, person 2 is in their own team, so on and so on, right? And now we have to handle 3 different types of queries. Types 1, 2, and 3, you can see down here. A type 1 query will merge the departments of X and Y. So you're going to get person X and person Y, and then whatever teams those are in, those teams are going to combine together to make one bigger team. So for example, maybe I merge 2 and 5 together, and now the teams will look like everyone's on their own team except 2 and 5 who are on the same team. The second type of query is going to be merging a consecutive range of teams. So for example, this time if I were to get 2 and 5, then not only would I make 2 and 5 in the same team, but also 3 and 4 will also get added to this team as well. This entire range will get combined together. And so that means that the final result would be 1, 6, 7, 8, 9, 10 are all in their own teams, and 2, 3, 4, 5 are in the same team as well. Notice how we actually remember these teams as we go along. So for example, if I were to merge 2 to 5 together, and then my next operation was to merge 5 to 9 together, now the final results, would anyone like to actually tell me? What would the final result be? So if I merge 2 to 5 together, and then I merge 5 to 9 together, what would the final teams look like?
Would it just be team 2 since that's the first number we start off with?
Could you say that again?
Sorry, would it just be team number 2?
That's
the first number we start off with.
So yeah, right, exactly right. Because it's out of 2 and 5, merge 5 and 9 together, then this whole thing just becomes one team, right? You can call it team number 2, I guess. But this whole range just becomes one team because these guys are a team, these guys are, and then we merge all of these together. So 6 joins this team, 7 joins that team, 8 joins that team, 9 joins that team. So this now just becomes one mega team, and of course 1 and 10 are by themselves. Does that kind of make sense to everyone? Does this question make sense? It's very important that it does make sense before we get on to the actual solving part. Maybe we'll go for an example, just to make things clear. Okay, so we have 8 people. So n is 8, and the number of queries you get is 6. Okay, so number of people, so our people is going to look like this. And so first what we're going to do, explain type 2 again. Yeah, we'll go for an example. So here, check if 2 and 5 are in the same team. Well, initially everyone's in their own team, so 2 and 5 are not in the same team. Answer is going to be no, which is what gets outputted here. type 1 query, we merge 2 and 5. So 2 and 5 are now on the same team. And then we once again ask if 2 and 5 are on the same team. This time the answer is yes, right? So I guess what we could do is we could keep a track of all the teams like this. And so after merging, so this is the beginning. Then we merge these teams like that. And then the result would be 2 and 5 like that. They should all be their own arrays, actually. Teams look like that. After we merge 2 and 5 together, then the teams are going to look like this. Yeah, then we check whether 2 and 5 are connected. Of course, they are in the same team now, so we output yes. Then we merge 4 to 7 together. So everyone, so 4, 5, and 6 and 7, the teams of all those people then get merged together. So here, this guy's team, team 4's team, team 5's team, which is this entire thing, team 6's team, which is this, team 7's team, they all get merged into one big team. So after this 2, 4, 7, our final teams are going to look like 4, 5, 6, 7. They all got merged into this one mega team here. And then you get removed from here. So this is what our teams are going to look like, right? So combine the team of 4, the team of 5, which is this, the team of 6, and the team of 7, all into one team, and this is going to be the final result. Here we combine teams 1 and 2. So the team of 1 is this guy, the team of 2 is this guy over here. So when we combine the two, 1 would just join this team. So we get something like this. And finally, check if 1 and 7 are in the same team. Well, we never explicitly added 1 and 7 together in any of these, but because we merge a bunch of teams together, then indirectly, 1 and 7 are now in the same team, right? You can see this here. So 1 and 7 are now in the same team, so our output is yes. Okay, tempo life seems satisfied. Is everyone else satisfied as well?
Yep.
Okay, great. So let's get started. So does anyone have any thoughts on this question first off? Honestly, I'm not really expecting too much because there's only 5 minutes of thinking time for you guys, but yeah, tempo life says map again. Not quite. I don't think for this question, maps would be very good. I think you're talking about like how to store these teams. The complexity would be too big. I'm not going to go into it because of time. But normally, if you were to actually try and store each of the teams separately, kind of like we did here, you're going to run into time issues because it's going to take up to like order n to like try to combine some of these teams. Kevin says, sounds like disjoint sets would be good for keeping tracks of teams. That's an awesome suggestion. Sam, did you have something you wanted to say as well?
I was just going to suggest maps too, but I think, yeah, n's way too big for it.
For sure. Okay, so yeah, so before I actually engage with what Kevin said, I did want to talk about something else that we could do. Now, actually, no, yeah, let's actually go with this. Let's go with this disjoint set thing. So great. The disjoint sets sounds like a great choice for this. So Kevin has obviously watched the lectures as well. Disjoint sets, if you guys don't know, solve a very similar problem to this. Disjoint sets, what they do, you have n individual, we'll call them people, right? And disjoint set unions rather can solve the following queries. So 1, merge 2 people together into the same group, and 2, query if 2 people are in the same group or not, which basically exactly correspond to queries 1, so merge 2 people together, and queries 3, which is, or is it? If type equals 3, then your task is whether they're in the same department. So DSUs actually exactly solve this question if we're only dealing with queries 1 and 3. Queries 1 and 3 only, then DSU is perfect. DSU has a very nice property in that when you merge 2 teams together, that is order inverse Ackermann n time. And order inverse Ackermann is like basically constant time. Something like 2 billion, inverse Ackermann of like 2 billion drops down to like 5 or something crazy like that. So using inverse Ackermann is basically constant time. So merging becomes constant time. So handling query ones become constant time. Handling queries threes also become constant time as well, because that's also inverse Ackermann. So what we get at the end of that is order constant time for all the queries of type 1 and type 3. There is one problem though, which is queries of type 2 here. So queries of type 2, you're going to need to merge potentially multiple teams together. Every single merge takes constant time. So what's the worst case complexity of a query of type 2? Can anyone tell me? So when would the worst case occur / what is the worst time complexity for handling query 2s with disjoint set union? And I'll just also write out what DSUs are for those who haven't seen the lecture, just so that you guys have something to look at as well. Okay, not sure. So let's have a look at this. Basically, when we get a team X to team Y, actually Tanit's absolutely got it. Worst case is n time, exactly right. The worst case will happen if X is like 1 and then Y is like n. Because what happens then is because we need to merge 1 and 2 together. So like team 1 and team 2 together. Then we need to merge team 2 and team 3 together. Then we need to merge team 3 and team 4 together, and team 4 and 5 and so on, right? You're gonna keep doing that all along the whole array. And so that's gonna actually take order n time in the worst case. So doing a disjoint set union in the worst case for query type 2, order n. And so in the worst case, if this entire input was really just queries of type 2 querying from 1 to n, then our worst case would become order qn, the complexity of our entire algorithm. And if you look at the bounds, n's 200,000, q is 500,000. If we do the maths, 200,000 times 500,000, let's chuck that into a calculator. That's going to be this massive number, which is 100 billion. That's going to be way too slow because remember the magic number that we have to deal with, the number of operations that a computer can run in a second is about 200 million. That should be the number that you should be aiming for. So if your number that you get is like orders of magnitude higher, then it's not going to run in time. And 100 billion is definitely not going to run in time. So you can't have an order qn solution. But we actually made some nice progress here. So this solution doesn't quite work, doesn't quite get the full solution, but it is a very, very nice first step. Okay, where to go from here? So what I was actually going to suggest, if we hadn't come across the DSU structure or DSU idea, was well, typically what you would do, right? From last week's sort of blueprint, we could try a brute force solution, right? We could start by trying out a brute force solution, try to see what a brute force solution might give us. In fact, in this case, DSU you could consider as a brute force solution as well, right? Because it works, it just takes a little too long for queries of type 2. Great. But what if the brute force solution now doesn't work, right? Where do we go from here? And so one other thing that I want to sort of highlight for you guys today in this question, one other technique that we can use for problem solving when we get stuck is to solve easier versions of the question. In fact, we've actually already kind of done this for our DSU solution. In our DSU solution, we have solved the question where we don't deal with questions 2, queries 2. We only deal with queries 1 and 3. right? That's one version, one easier version of the question. And so we can actually apply the same thing again for this particular question, which is what if we could only handle queries 2 and 3, right? The solution for queries 1 and 3 only. Let's ask ourselves an easier question again. What is the solution for handling queries 2 and 3 only? So if we just never got queries of type 1. These types of questions where you have multiple different types of queries are really well suited to this paradigm of solving an easier question, because all you can do, you can just ignore some of these queries and try to solve for some of them. And in that way, that gets us to a better solution. Other questions might get us different ways of solving easier versions of the question. It all really depends on the question itself. But definitely for sure, solving easier versions of the question can help you guys. This is basically what subtasks are for, by the way. We're basically making our own subtasks. Okay, so here's my sort of suggestion for you guys. Let's try and solve queries 2 and 3 only this time. So now we don't really bother with merging like team X and team Y, where they're like halfway across the entire department. Now we're only merging consecutive ranges of teams, right? And then querying whether they are in the same team or not. So what do you guys think? Have a think about this. How might we solve this question, and or what observations can we make about the teams if we're only handling queries 2 and 3? What kind of observations can we make if we're only handling teams 2 and 3? Queries 2 and 3, sorry.
Would using a tree structure be easy to kind of combine nodes and then query nodes?
Using a tree structure. It's not ideal either.
Yeah.
Who's that in the background?
Oh, that's just my housemate.
He's just helping you out.
Yeah. Oh no, he's talking to someone on the phone.
All right. Yeah. So a tree structure, it's a cool idea of how to store the teams in a different way. But ultimately, I think you'll find if you try to do a tree structure, you come across the same complexity issues that you came across just by using maps or just by using even DSUs, which is that when you're merging teams together, still, oh my goodness, you can draw on the screen to me. I will need to somehow disable that. Okay, I don't really know how to disable it. I'll just leave it there. But yeah, if you use a tree structure, same as the map and same with DSU, I think you'll come across the same sort of issues when it comes to, yeah, all good to me. When it comes to merging the teams together, which is that for every team that you merge, you still need to like merge, like go down into the tree and merge the individual nodes together, right?
Yep, makes sense.
Mm-hmm. Okay. So let's have me give you a hint about the observation. So with the observation in particular, let me ask you a question. What will these teams look like? Is there any sort of pattern that you can find with the teams if you're only dealing with queries 2? If you're only merging consecutive ranges of people, is there going to be some sort of pattern with what the teams look like if we do that? Especially compared to if we allowed query 1s, where we can merge teams from like different locations. What might our teams look like? Is there any special pattern that our teams will look like?
Well, their count's going to be limited by the range n that you want to essentially merge them with.
What do you mean by their counts?
Well, I mean, like I guess the number of members, if you're taking that example, if you're merging teams 1 and 2, then you know the count's going to be, I guess, limited. Oh, I guess that doesn't really help us. I was going to say that it's going to be limited by that amount, but
Yeah, so that is an observation, but yeah, as you pointed out, it's not really that helpful to us. We don't really care about the counts of the teams. We only care about whether two people are on the same team or not. Ken makes a great suggestion here. People in the same team will have consecutive numbers. That's exactly what I was looking for. So as it turns out, if you only use these types of merges, so merge consecutive values, then every single person in the team is always going to have consecutive numbers, right? You're merging ranges together. Another way of thinking about this is all your teams will just form ranges in this thing here. So initially, all the ranges are going to be like one-off. So like you have like one single range for one single range for two, one single range for three, so on and so on and so on. So maybe I'll like represent this as like this. So like this line indicates that every person is their own range. But then maybe if I merge like teams 4 to 7 together, then this whole thing becomes one range, right? And so the teams kind of look like this, right? And then maybe if I merge teams 2 and 3 together, then they join the same range like this. And if I merge teams 3 to 5 together, then maybe this whole range becomes one. But basically the idea is that these teams are basically just going to form ranges on our number line. Does this observation kind of make sense to everyone? I'm sure if you have a little bit of time for yourself, you can actually prove a little bit more formally why this is true. But yeah, this intuitively kind of makes sense because every time we merge people together, we merge everyone in between as well. That's why our teams are always going to be ranges. And since our teams are going to be ranges, it actually makes a lot of sense to actually try and store our teams as ranges, right? So this time, maybe this was not as useful before because I guess the main issue would have been merging teams. So when you merge teams, you would need to like find which teams like everyone is because this isn't necessarily sorted. So you need to find which teams everyone's in, and then you need to actually like manually move all of them into like one list, right? And that's the order. That's where the order n comes from. And so that's why that can be a little bit annoying if you're using this sort of thing, this sort of representation for originally. But now, if we're storing ranges kind of like this, so maybe like 1, 1 to 1, 2 to 3. Let's go back to like this one. 2 to 3, 4 to 7, 8 to 8. Now what we can do, instead of actually like moving like individual peoples between teams, we can work with ranges, which hopefully will be a little bit faster because each range actually allows us to deal with multiple people at the same time. So here I'm having some sort of data structure that's going to store my ranges. And so if I were to merge like 3 and 5 together, essentially what I'm doing, if we look at our sort of range representation here, what I'm doing is I'm finding the team that, oh, let's actually do it a little bit differently. Let's go, let's say I had this because I want to demonstrate a point here. Let's say our teams are 2 to 3, 1, 2 to 3, 4 to 5, and then 6 to 7. And then let's say I want to merge people 3 to 7 together, right? Essentially what I'm doing in my range interpretation here is that I'm looking for the first element, the first pair that's going to be less than or equal to the 3. So 3 to 7. Yeah, let me write this out. So merge 3 to 7. Find the first pair that is less than or equal to 3. 2, find the first pair that is less than or equal to 7. In other words, I'm finding the teams that 3 and 7 are in. So 2 to 3 and 6 to 7. Those are the pairs that correspond to these two. Then essentially what I'm doing is I'm deleting every single pair in between and then inserting a new pair, a new range that covers the whole thing. So delete every range in between and replace with one new range, right? So I'm deleting this, I'm deleting this, I'm deleting this, and I'm going to replace this with one big range, 2 to 7, right? And that's going to and that's going to update our range nicely. And now if we want to handle queries of type 3, what we can do is we can do this thing again, find the first pair of like an element that's going to tell us what team it's in, find the team of the second element, And if it's the same team, right, if the ranges are exactly the same, then we can say that they are in the same team. Okay, does that, hopefully that kind of makes sense to everyone. And also, I guess my next follow-up question would be, what kind of data structure might we use to store these ranges? Hopefully, if it doesn't make sense, getting the data structure is going to make this a little bit more solid, because I'm talking a little bit abstract right now, but what kind of data structure might be useful here? In particular, it needs to support finding something that's less than or equal to, find something that's less than or equal to, deleting elements in the thing, and also inserting a new one, inserting a new element. What do you guys think? What kind of data structure might be useful here? Yeah, Tanit's actually exactly got it. A set. Perfect. A set, if you remember, actually handles all of these things for us. In a set here, we can do lower bound to find greater than equal to or greater. And then if we find the iterator to the first thing that's greater than and then subtract 1, we're going to get the first thing that's less than or equal to, right? So that's actually how we can get the less than or equal to thing with the upper bound. And of course, everything else is really easy as well. So we can use the upper bound to find stuff. We can use the erase and insert to erase things from our set and insert things into our set. And finally, we can also use the iterator, right? Because these are all return iterators, the s.find, remember? And so since we're deleting everything in between, we can actually use this iterator to loop through and delete everything in between for us, right? So sets are the perfect use case for this example here. The sets are the perfect use case. And so let me break this down a little bit further. So first things first, when it comes down to implementation, we can store it like this, but it's actually a lot easier just to store the beginning numbers of every single range. These secondary numbers, they're kind of useless because they're always just going to be one less than the next number, right? So one thing we can do to make our lives a little bit easier is instead of storing the whole range, we just store the beginning of the range. And then we use the next number to indicate where this range ends, right? So if we went back to what we had before, our ranges would have looked like this, right? That corresponds to here. And then basically what we do, we use the upper bound technique that I talked about to find the first thing that's less than or equal to. So that's this 2. We use the upper bound to find this first thing that's less than equal to the 7, which is the 6. And then we use an iterator to loop through all of these. And basically what we're doing, we're just removing everything that's not the first one, right? Remove everything that's not the first, and that has the same effect as combining all of these ranges down into one range. Of course, every single erasure is order log n. And finding elements is order log n as well. So yeah. Does this kind of make sense to everyone? Does this sort of set implementation make sense? Or are there any questions? I'll talk a little bit more about the time complexity afterwards, but for now, does this set solution kind of, at least on the surface, make sense? Great. Okay, so let's quickly talk about time complexity. What's the worst case time complexity for a single query? This is a good question to think about as well. What's the worst case time complexity for a single query? As a reminder, upper bound is log n, inserting is log n, and erasing is log n. Kevin makes a, yeah, Kevin perfectly. Kevin Anthony, both get it correct. Though Kevin is, of course, more specific, so he gets the full marks here. Very nice. Because Kevin has predicted my actual follow-up question as well. The answer to this question is n log n. The worst case to handle a single query is going to be n log n. Because, for example, if we have to merge everything from 1 to 8 together, right? Then we're going to have to erase everything, right? We have to erase the n-1 elements. So that's going to give us order n log n, right? And so our final complexity, quote unquote, final complexity is going to be Q n log n. We've already worked out that order Qn is going to be too slow. So in theory, you might ask yourself, isn't order Qn log n going to be too slow as well? Isn't this going to be too slow? But then, of course, Kevin points out very astutely, well spotted, Kevin, which is that every single query after, if we erase everything, right? So if we get like the worst case possible, we have to erase everything in our set except the first element. Then every single query after that is going to be order one time because there's nothing left to erase, right? Or technically order log n time because we still have to do the finding stuff, right? The upper bound stuff, that's still going to be log n. But every single thing after that is going to be log n. So basically what this is kind of telling us is that this is kind of give us a hint that like if we have like a particularly bad case, then stuff gets like smaller like later on. Another way of thinking about this is that you have a set that contains initially all n elements and you're erasing from it one at a time, but every single element can only get erased at most once, right? So it doesn't really matter what the worst case about erase is going to be. Yes, in theory, in one go, you could erase like all of them in one go, but over the runtime of our program, every single element is just going to get erased at most once. And so this is what we call amortized complexity. So this is, so let's get rid of this. This is wrong. Wrong, I'll mark that as. This is amortized n log n for the erase, right? Oops, spelled like that. Amortized n log n means that it's not per query, it's just over the runtime of our program. This erase part is going to take, this erase part here, sorry, is going to take n log n in total. And of course, each of these residues, so this one's log n, this one's log n. And if I separate the insertion as well, this part is log n as well. So let me write out these complexities. But then this, delete every single range in between, is amortized n log n. And so what we'll get as our final complexity is going to be, oops, not amortized, is going to be order n log n plus q log n. And you can sum in these values, 500,000 and 200,000. But typically, if everything is on the order of 100,000s, then n log n and q log n solutions will work. So I'm not, you can do the calculus for yourself, but I can tell you that this will run in time. Great. So now we have this concept of amortized complexity as well as the actual complexity per query. And of course, when it comes to querying whether two people are on the same team or not, we can just apply this first pair thing. So you can do the upper bound search to find the team of person one and the team of person two. And then you can just check if that's the same person. And if it is, then they are on the same team. If it's not, then they're on different teams. Okay, excellent stuff. So this is going to solve queries 2 and 3. Why doesn't this really work for query 1? Why can we not apply the same thing to queries of type 1? Not sure? Well, really the main reason we can't apply this to query of type 1 as well is because if we allow queries of type 1, we break that condition where all the teams are like consecutive people, right? Now the teams are no longer like really nice ranges. Instead, maybe like this range is connected to this range and they're on the same team, right? So we lose that very nice property that allowed us to do this in the first place. Okay, so that's a little bit unfortunate, but we actually have once again made progress. So to handle, just to recap, to handle queries 1 and 3, we can use DSUs, disjoint set union. And to handle queries 2 and 3 only, we can use a set, right? We can store a set of ranges and update those as we go. What do you guys think? Given that we have these sort of 2 solutions to 2 easier versions of the problem, can you guys think of a way that we might be able to solve the full problem then? And once again, I'll give you a moment to think about it. So ideally, you want to be making use of both of our observations from our two easier problems, right? So maybe somehow using the DSU and our sets together.
Could we check for common elements and combine them?
Check for common elements and combine them. So what do you mean by that? What type of query is this, firstly, that you're handling?
No, sorry. Yeah, sorry. My bad. I was thinking of the wrong thing.
Oh, good. All right. Help you guys out a little bit here, since you guys are struggling a little bit. The way that we can actually solve the full problem, as I said, is to actually just apply our DSU on top of our set structure. Okay, so what do I mean by that? So we have this very nice set structure here. Yeah, which is going to store like the leftmost person of a team, right? And this is going to work for queries of type 2. And so let's try and modify this to work with queries of type 1 now, right? And naturally, of course, as we sort of worked out earlier, DSUs are a perfect fit for handling queries of type 1. So why not let's try actually applying a DSU just on top of this structure as well. Can anyone figure out how we might use a DSU on top of this to handle queries of type 2? So obviously DSUs will handle the queries of type 1, but how are we going to apply the DSU to handle queries of type 2 for this kind of structure as well? Where might we slot it into this sort of set of instructions that we've got here? Not sure? Okay, well, to help you guys out, basically what we can do is when we're deleting all the ranges in between, we can just merge them together in our DSU, right? So I'm actually going to copy this and like put it in its own section. So type 2 queries are going to look like this. Let's make this a little bit more general. So we're going to find the first thing that is less than, or first person that is less than or equal to X, and the first person that's less than or equal to Y. This is going to represent their quote unquote representative of like the team ranges, right? Then we're going to delete every single range in between in amortize and log n time. And while we're doing that, we're going to merge them together, right? Because these, like every single like range that we're deleting, we're merging into our first range, right? We're merging them all into one big group. And finally, in our actual set, we can replace it with the new range. Since we're doing this sort of one thing, we don't actually do that. And so we're just deleting every element in between, except the first. So yeah, updating it with our new sort of set structure, which is not storing the end of our ranges. This is what our program will look like. So of course, deleting every single element, we get that amortize and log n, and every single deletion will also add a near constant time thing from our DSU as well. So this is amortized order n over here as well. We don't really need to think about it because this is already overshadowed by this amortized and log n there. So this won't really affect our complexity too much or at all. Okay, type 1 queries then becomes just merging them in our DSU. This is near constant time. And then finally, type 3 queries become equivalent to checking our DSU to see if they are connected. Because remember, with the help of our set structure here, we're now actually merging the consecutive teams together as well. We're handling queries of type 2 efficiently. And that's why we can now use the DSU for queries of type 3. So that's kind of the full solution. Does that make sense to everyone? At least a little bit of sense. I know it might seem a little bit confusing right now. Hopefully it will get cleared up when we get into the coding segment. But yeah, I guess the main point of this is that we started out with a DSU. We noticed that it didn't really quite work for queries 2 because it would take too long. It's order n worst case. We came out with the set solution and realized that the set solution gave us amortized n log n when it came to merging ranges. And then we realized that we could actually apply the DSU concept onto that, like piggyback off of that amortized n log n complexity with our DSUs in order to get that DSU complexity down to amortized order n instead of order n for every single query. And so I guess the takeaway from this question is once again, when you get stuck on a question, brute force is one way that you can apply it, but another thing that you can try is solving easier versions of the question, because it was solely by solving easier versions of the question that we kind of made a natural path towards the full solution. Trying to visualize deleting and merging in the DSU. So that's the thing. So the DSU is only merging. You do not delete in the DSU at all. The only thing that we're going to be deleting from in the solution is going to be the set, right? We're going to delete from the set, and in that case, and then we're going to use those. We're going to use whatever we delete from the set to merge in our DSU. Maybe it'd be better if I go for an example. I think this will make a lot more sense if we go for an example. Okay, so our solution is going to be a combination of sets and DSU. So let's go through it. So here we have the same sample before. So 1, 2, 3, 4, 5, 6, 7, 8, like that. This time we're going to store our set. Yeah, so merge what is deleted, exactly right. So this is what I'm going to set, our set is going to look like. Okay. So every person has their own range. And of course, in our DSU, everyone is not connected, right? So I guess I'll bring back our initial sort of DSU. It's gonna look like this. Okay. So check if 2 and 5 are connected. Well, in our DSU, we can check that in constant time. So 2 and 5 are not connected. So print out a node there. Connect 2 and 5 together. So this is a type 1 query. Type 1 queries we handle only in the DSU. We don't update the set. So what this is going to look like is 2 and 5 get connected together, but our set remains the same, right? There's no way we can really update our set. Our set is only for considering consecutive ranges of people. Okay, 3, 2, and 5. So we can check out DSU once again in near constant time. That's just going to tell us that 2 and 5 are in the same team. So we're going to print out a yes. Okay, here comes the hard part. Combining ranges 2, 4, and 7 together. Combining ranges from 4 to 7 together. So here, what we're going to do, we're going to look into our set. We're going to find the representative of 4 and the representative of 7, right? In this case, it's just 4 and 7. We can use the upper bound trick to do that. And so what this means is that basically we're going to delete every single element in between, excluding that first element 4 here. Notice that if we do that, then it's essentially the same as merging all those ranges together, right, in our set. So this range now goes from 4 to 7, which is right before the 8. So basically merging these ranges together. And so what I'm going to do, we're just going to iterate through these. So we're going to delete the 5, and we're going to merge that into the 4 in our DSU. So here, this 5, this set 5, and this set 4 are going to get merged together. So now it's going to look like this. So we merged the team 5 into team 4, merged team 6 into team 4. So delete that as well. This is what our DSU is going to look like. And then finally, merge team 7 into team 4 as well. So delete this and merge into that like that. So you can see that we've done a bunch of merges in our DSU. So now our DSU is once again updated correctly. 4, 2, 5, 6, and 7 are all on the same team. And our set is also being updated correctly as well, because now we're making sure that everyone from 4 to 7 are in the same range. We've basically merged them down, combined them into one big range, which is going to help our time complexity. So once again, we do this merge again. So merge 1 to 2 together. This corresponds to 1 and 2 here. We're going to delete the 2 and then merge team 2 into team 1. Right, so we can do that in our DSU, once again, in constant time, near constant time. Like that, our DSU is going to look like this. Our set's going to look like this. And finally, when you check if 1 and 7 are in the same team, then you can check 1 and 7 like that. And the answer will be yes. Okay, so hopefully this makes a little bit more sense now. This set is going to store consecutive ranges. It is possible that like separate ranges are the same team. So for example, ranges 1 to 2 and ranges 4 to 7 are in the same team. That information we can't really encode in our set, but we can encode in our DSU. And so that's why this DSU is going to keep track of that. The reason why we keep our set is so that we get that nice amortized complexity for our DSU. We're making sure we're not constantly merging like every single person together. Rather, every time we merge someone in our type 2 query, we can sort of compress that down into one range, which makes it a lot easier for our DSU to handle. Okay, hopefully that makes a little bit more sense. Let's get into coding. I am running out of time, so I would like to speed things up a little bit here. So let's start with our classic headers. We'll also need a set. We'll also need, what else will we need? Let me grab my sample code. Yes, we'll need an iterator, and I think we'll need an algorithm as well. Yeah, we do need an algorithm. Okay. Find the maximum number of people as 200,000. So this is a nice thing that we can do. We can define a constant max n. So this hash defines a constant max n. And every single time I type in max n, it's going to get replaced with a 200,005 in compile time. So that's going to be a useful constant for us. First thing we need to do, we need to implement a DSU. I'll leave the implementation details up to the lecture. I'm sure they'll explain it a little bit better than what I can do. And of course, for the interest of time, I'm going to have to go fast as well. But really, all you really need to understand about it is that every single element has its own root. I'm going to be making sure we update the root in order to indicate that multiple elements are on the same team. If multiple elements are in the same group, then they'll have the same root. And if they are not, then they'll have a different root. So void init. The root of every single element, we're just going to set to itself for now, which means that everyone's on a different team initially. I want to set the size of each of these groups to 1. Okay. Get root. So this is going to be our get root function. We want to find the root of an element. If the root of element is itself, then we can just return x. It's its own root. Otherwise, we're going to return get root of x. What it's going to do, you can kind of think of it as like a little bit of like a tree structure. It's going to find the root and recurse down and down. So we're going to keep finding the root until we get to the beginning. And also one nice optimization trick that we can do is once we've found the root, we'll also update our current root to be equal to whatever we found down the recursion. That way, future calls will have the root updated very nicely for us. Let's merge two things now. So merging A and B together. First, we will find the roots of both of these. If A is equal to B, then they're already merged, right? Their roots are already the same, so we can not merge them. If size of A is smaller than size of B, then we'll swap A and B. And what this gives us the nice benefit of having is that now, if we reach this part of our code, size B is always going to be smaller than size A. One nice optimization trick for union find or DSU is that we always want to merge the smaller group into our larger group. And this will actually give us a very nice complexity. This swap function is from the algorithm, which is why I included it. It basically gets these two elements and swaps the values of them. Very handy function so that you don't need to write like 3 lines. So size of B is going to be stored and equal to size of A at this point. then we can just set root of B is equal to A. So connect B onto A. And then we also make sure we update the size as well. So size of A plus equals to size of B. Great. That's going to be our DSU. And let's head into our main function now. For this particular question, you don't always need to do this, but when I was implementing, I found that this particular question required this. You're going to need to speed up your IO. So you're going to need to include these two lines of code at the top of your code. This is going to make sure that CIN and COUT run fast enough. By default, scanf and printf are the fastest. CIN and COUT are a little bit slower, but we can make CIN and COUT behave the same as scanf and printf by adding these two lines, and that'll make them faster. For most problems, this won't be an issue, but there are going to be some problems, especially with large input sizes, where this code is going to be necessary to make sure that your program will run in time and not time out during when it's run. Okay, so include those lines. You should just include those lines of code whenever you use CIN and COUT. It's just a good practice to do so you don't forget. First, we're going to initialize our DSU from our function up here. Then we're going to scan in our input. So int n q, cin n, cin q. Then we're going to define a set s or int I equals 0. And we're going to initialize it to just 0 to n minus 1. One thing we're going to do, we're going to do 0 index everything. So when they tell us to merge 2 and 5 together, in our code, we're really going to merge teams 1 and 4 together. So instead of 1 indexing, we're going to 0 index. Okay. I0, I1, Q, I++. So we're going to loop through our queries. I'm going to scan in T and X and Y, and we're just going to subtract 1 from both X and Y, just to make sure that we're 0 indexing instead of 1 indexing. Let's handle all of our different query types now. So if t equals 1, then we do something. If t equals 2, we do something. Else if t equals 3, then we do something. Okay. Our first one is going to be just simply merging X and Y. And that's as simple as just calling our function in the DSU. And that's just going to merge our two groups together. Great. Let's handle t equals 3 as well, because that's the simplest one. So if get root of X is equal to get root of Y, then they are in the same group. We can print out yes. Otherwise, we can just print out no, like that. And finally, we have our middle point here. So check X and Y in the same team. We have a middle point where we can just find the, we can do the erasing thing and merging thing. So merge team X, X+1, team Y. Okay, so in this case, we're just gonna declare an iterator. We're going to call it. I'm gonna set it to the upper bound of X. So remember, the starting point is going to be the what was it? Yeah, the starting point is going to be the first element that's more than or equal to X. So to get that, we find the upper bound and then we subtract 1 to get to that starting point. Since we're going to be deleting from 1 after the starting point, we're going to add that 1 back on again. So it's going to cancel out. So we're just going to be interested in the upper bound of X. Now, while iterator doesn't equal to s.end and our iterator is smaller than or equal to Y. So in other words, because we're looping through our set here, we want to stop as soon as our iterator, we get to an element that is greater than Y, right? Because then that's a team that we didn't want to merge together. Then what we'll do, we'll merge X, which is the first person, the team of the first person, and whatever was pointed to by our iterator, make sure we do reference that. And then we'll make sure to erase our iterator, as well as add 1 to it as well. This part here is a very nice shorthand. Essentially what we're doing, because one of the things about erasing is that I could just do this, or I could try to do this, but this doesn't work because when I erase the iterator gets deleted, right? So now it++ doesn't really make sense because this iterator isn't actually pointing to anything in my set. That's a bit of a bummer. What I should do instead is I should set, okay, make a new iterator. I'm going to use the auto keyword. Auto just means it will set the type automatically for me, so I don't actually have to think about typing this whole thing out. Auto it2 equals it, it++ or it+1. That's the next it, I believe. So auto it2 equals to the next of it, then we delete it, and then now we set it equals to it2. That's kind of the long way of typing it out. That's what we should do. We should make a backup of the next element, erase our current element, and then set our current iterator to the next one. But a nice simple trick that we can actually do here is it++, and that's actually going to handle it for us. It++ is going to return our element and then increment it. So this is actually going to very nicely not only delete our current element, but move on to the next one. Okay. And so what this is going to do, it's going to do our array, our set deletions, as well as merge them all together with person X, which means that everything that we deleted is going to be merged into one big team. Let's go ahead and try this on the input. So why am I printing out a number? Oh, I am in Ghost again. Whoops. I keep doing this. Every single time I run it, and I just got like a weird thing. And like half the time it's just because I'm just running in the wrong directory, so I'm just compiling the old problem instead of the new one. Okay. I need to make sure to actually scan in my values here. No, yes, excellent. And I think that's the only test case. So once again, if it was an actual contest, you would just go ahead and submit this, and you would check to see if you get full marks. Once again, I'm going to ask you guys to trust me here. This is going to be the correct solution. I know because I've practiced this solution beforehand, so I know it works, and I haven't really missed any the little tricks or implementation details. And hopefully, if I submit this, I'll get full marks, but who knows? Anyway, that pretty much concludes the solution for company, as well as pretty much the entire tutorial. Are there any final questions about Restructuring Company, the code, or the question solution itself? Okay, very nice. Once again, sorry for going a little bit over time. There's just so much content to cover in these tutorials. I honestly very much struggle to get things like in time, but because there's just so much stuff that you need to cover, especially everyone's new to C++, everyone's new to cognitive programming. There's a lot of extra stuff that needs to get talked about as well. Hopefully this gets settled down a little bit in the next couple of weeks, where I don't have to do as much explanations for everything, and you guys will kind of just know what's going on without me needing to explain fully. But yeah, I guess that's pretty much it. What we'll do now is we'll head into our labs. So once again, I'll set up the breakout rooms. As a reminder, rooms 1 to A to E are going to be for the problem that you're on. So regardless of whether you're doing problem set 1 or hopefully problem set 2 is released. I haven't checked yet. Yeah, problem set 2 has also been released, I believe. So regardless of whether you're doing problem set 1 or 2, go into the room that corresponds to the problem that you are working on. If you don't want to get disturbed, then you can go to the quiet room. And finally, I'll be hanging out in Kevin's corner. If there's no one there and you want help, head on over to Kevin's corner. Otherwise, periodically I'll go around and just check up on all of the rooms, check how you guys are going. Okay, I think that's pretty much it. Yeah, okay, that's pretty much it. I'm gonna just set up the breakout groups now. Okay. All right, thanks very much for coming for the tutorials, and I will see you guys in the labs.